So they record the data, whether it's a success or not a success or a failure, whatever you want to call it, for that particular, let's say, well that they witch. Now, this is kind of a problem. I don't know. We haven't maybe exactly dealt with the kind of problem like this, which I think makes it a good problem. And there's a lot of approaches that you can take. So I'm not necessarily saying that this approach is the only correct approach that I'm going to do, but it's certainly an approach that I think makes sense, and I think is not actually the most difficult approach. So I will try and make very clear exactly what we're going to do and the assumptions that I'm going to make. So are there any questions about the setup of the question before I try and solve it? Okay. So we have essentially witched wells and we have witched wells and we have unwitched wells. Now they tell us that there are 29 witched wells, so I'm going to write n is 29 for the witched wells, and then the unwitched wells I'm going to call m, the sample size there, which is 32. And I think I counted this right. Hopefully I didn't mess up. But there are both 5 unsuccessful attempts in either of them. So there are 5 U's in this one, and therefore there are 24 successes, and 5 U's in this one, and 27 successes in this one. Now immediately, probably the whole first thing that comes to your mind is okay, well, we can try and compare the proportion of these. So the proportion of successes in this one, which I'll call PW, hat, in this case is 24 over 29, right? And this is I'm going to assume that they're, okay, we'll say afterwards. And then PU hat here is going to be 27 over 32. And so I'm going to essentially make an assumption that every time we sink a new well, it's independent of the previous times we did it. So my assumptions. Every time we sink a new well, it's independent. Which in reality may or may not be true, but I think that's without this, it's essentially a very difficult problem to do. So I sink a well and I go somewhere else, it's independent of that. And given a method, whether we do unwitched or unwitched, given whether we do unwitched or witched, the probability of success is the same. Probability. I missed the B and I. So that means there's an overall probability of when I witch a well that I get a water or not every single time I go and sink a well, and same with unwitched, and they may or may not be different. So denote those true values without a hat, PW and PU. Okay. Now, what does that mean? Essentially, the test that I can do in this case is I can just test whether PW, the true probability from witching a well that we actually get a success, equals the true probability of when we don't witch a well that it has a success. What is this? Equivalently, of course, we can write this as PW minus PU equals 0. So this probably looks like a common setup, like we did with 2-sample testing. This is kind of a special case of that. And the reason why is, so I'm going to denote a success as 1 and a failure as a 0, essentially. And I'll denote the data from the witching as the xi's, I equals 1 to 29, and the data from unwitched as the yi, so I equals 1 to 32. And so in this case, based on all of my essential assumptions here, I've essentially given a distribution to both xi and yi if they're 1s and 0s. So xi is going to be Bernoulli PW, and yi is going to be Bernoulli PU based on the previous definitions, and I assume they're all independent. Okay, are there any questions so far on what I just talked about? Okay, great. So typically when we've done like t-tests and such, we have had Gaussian data. Now, like Bernoulli data is not really Gaussian data, but it essentially lends itself in a nicer way than with t-tests. And the reason why is because the variance of Bernoulli data is also in terms of PW, and we assume something about PW or PU under the null hypothesis. So we don't need to separately estimate the variance. It is essentially pre-specified under the null for us. But this will essentially use asymptotic theory, my solution at least. I don't know about a specific other solution, but I think the solution makes sense. So let's think about that. So if we see what these p hat w and the p hat u's are, these are just the sample means. When we just count them as zeros and ones for the successes, for the failures and successes. So essentially, based on the previous data, x bar equals p hat w. This is like the proportion of successes, right? And y bar p hat u. So naturally, for this null hypothesis that I have, I'm going to use these as a test statistic, essentially. I'm going to use x bar minus y bar as a test statistic. Okay. Now, we have a fair amount of data, like 29 and 32, which I think is decently sized. So we're going to essentially use the CLT. We know that like x bar and y bar are approximately normal. And they're independent from each other. So we know that this implies that x bar minus y bar will also be normal because it's a linear combination of two independent normal random variables. And so all we have to do is just compute their mean and the variance that they each give us, and it won't make it. So I can actually figure it out. So first things first, we're going to compute the mean. And so the mean of this is just this, which is just this, and each of these x bar and y bar are both unbiased estimates for the true proportion. So this is just going to be equal to, I think it's w for x and u for y. So that's the mean, the true mean of this distribution, asymptotically. Are there any questions about that? Okay. So then the variance of this difference here, well, this is just the sum of the variances because their covariance is going to be 0. So normally we would have a -2 covariance x bar y bar, but we assume that the both samples are independent. So because of that, this is just 0. And so the variance of x bar in this case is the variance of the sample mean, which is equal to 1 over n squared, the sum of the variances, because again, I assume they're independent, and because they are Bernoulli data, these variances here is simply p1 minus p. So this becomes the sum, and the xi's are pw 1 minus pw. And so this just becomes pw 1 minus pw over n. Are there any questions about this calculation? And then obviously, we're going to need to also compute the variance of y bar. And I think I said it's n, right? Hopefully I'm. Yep. And so at this point now, we're just going to compute also the variance of y bar, which is the exact same computation, but we just switch the p and we switch the n for an m. So I'm just going to shift this down here. But we have that this is just going to be equal to pw 1 minus pw over m. Okay, and that's that. I will. Okay. So now we can just see essentially what the distribution of x bar is. I'm just going to write this as pw. just this here. That's supposed to be an M. And so now we have essentially the complete distribution of this x bar minus y bar. So using this, we have that x bar minus y bar subtracted by its mean, which is PW minus PU, and divided by the square root of its variance. So I have here, the square root of this is going to be approximately normal 0, 1. Now, typically when we have something like a t-test, for instance, we have this with an exact distribution, and then we just have to replace the variance with something like a sample variance, and then we get the exact t-distribution as a result. In this case, I'm making an approximation here with the CLT for these means, these sample means. And so I'm not going to switch to t-distribution ever because it's asymptotic. But I'm going to now keep going essentially with the test now. So under the null, we have, of course, that PW equals PU0, or PW minus PU is equal to 0. So under the null, I have that x bar minus y bar divided by this variance here is essentially what we're interested in. However, I don't have the individual values. All I have is that they're equal to each other. So we're going to essentially estimate them in a way that makes sense. So how do we estimate PW? Well, we know they're equal under the null. So I want to essentially only have one estimate for both of them because under the null they're equal. So the way that we can do that is we would just pool the samples essentially to create our best estimate under the null. And what that means is I'm going to take all of the successes from both of them and divide by all of the trials. So this equals the total number of successes divided by the total number of trials. And that's going to be our overall estimate for p hat, or best estimate of the null for the true value. And in this case, that is the total number of trials is 61, and there were only 10 failures, so it's 51 over 61 is our best guess essentially for p. Are there any questions so far? Okay, great. So then under the null, of course, we're going to essentially have this here, M. We have this here again, but I'm going to replace all of these with p hats. And now all of this is computable. We know everything, and this is still approximately normal 0, 1. So this is essentially our test statistic in this case. And hopefully the most rational thing to do if we want to see if there is a difference is we can just do a two-sided test, for instance. We can see whichever, because we have no reason to believe one way or the other, really. It might be worse to wish the well. So we're just going to do a two-sided test, essentially, to see whether or not there is a difference. And so we've done this, I think we've done a normal test a lot, but so if I just call this test statistic like T or something, if we want to compute the rejection region, let's say, we simply need the probability under the null that I'm going to do two-sided test, so we're going to have C alpha is less than or equal to T. Sorry. Want the probability under the null of rejecting, we want this to be equal to alpha. We want to restrict a type 1 error. I wouldn't do a t-test in this case because of the fact that this data is not normally distributed, at all, right? It's zeros and ones, essentially. It's successes and failures. So there's really no reason to use a t-test. We have no Gaussian assumption essentially. So I am going to just use essentially what is an easier test. I'm not estimating like the sample variance, for instance. So I'm not actually going to have like any t distribution guarantees because it's not normally distributed. So I'm going to just straight up use like asymptotic distributions for normality.
Okay, so even if the normal assumption is not valid, because that's asymptotic.
I mean, yeah, this is asymptotic. Like X bar and Y bar will be kind of close to normal because they're sample means.
Okay, that makes sense. Thank you.
Yeah, of course. One hell, yeah.
Yeah, but I think the X bar and Y bar, if we apply CLT, they are normally distributed, right?
That's true. But in order to use t-tests, you still need like the data itself being normally distributed because like the sample variance needs to be chi-squared, and that only happens if the actual data points are normally distributed.
Okay.
So each observation would have to be like we have to assume each observation comes from a Gaussian distribution.
For the t-test to be like technically valid, yes, but like people do that without that assumption all the time. But this is like an extreme. Like the data is not very. It's like bimodal data. It's not even close to Gaussian really. So that's why it kind of doesn't. Yeah.
Also, this I've seen this before, but is this the same as a two-sample proportion test?
Yeah, this is a two-sample proportion test. It's the same thing.
Okay.
Yeah. So that's essentially what this is. I'm just trying. I don't think we've learned that, so I'm just trying to like derive it essentially. Mm-hmm. Yeah. So like, moving on, like what we have, unless there are any more questions, sorry. So like essentially what we have here is this is not like a normal setup that we usually use for testing. So we want the probability of rejecting under null to be equal to alpha, whatever alpha level is. And so we're going to reject for like large or extreme values of this t. So I'm going to like essentially flip this to be 1 minus probability of not rejecting. And so we're not going to reject for some interval that I'll call like C alpha and K alpha. And so essentially I'm going to need this to be true. And we have, this is a normal distribution essentially 0, 1. So we can just pick C alpha equal to Z alpha over 2 and K alpha equal to Z1 minus alpha over 2. These are the standard normal quantiles. And that will hold. So these are like approximately like negative 1.96 and 1.96 respectively. And so we could just compute this with all the values that we have. And if it falls outside of this region, we reject. So reject if t is less than C alpha or t is greater than K alpha, which essentially tells you whether like the absolute value of t is greater than C alpha or Z1 minus alpha over 2, which equals like Z1 minus alpha over 2. Are there any questions about this problem?
Sorry, Josh. Can you go back to where we were talking about the t-test thing?
Yes. I didn't write it anywhere, but yeah, we can talk about it.
So isn't X bar minus Y bar normally distributed, and we are estimating their variance?
Yes, that's true.
And then usually under that condition, we wouldn't just do t-test.
We would usually do t-test, but like there's like we're throwing out information in that sense because we know that we know how to better estimate the variance with this method, like with this exact form of the variance than with the sample variance, in a sense.
Right.
Because that is not normal. Like it wouldn't make sense for me to use like the sample variance to estimate the variance here because that is not normally distributed, or like we don't know, like we know the form of the data. So technically, I guess you could use a t-test in this case, but it's like a huge jump, and it doesn't really hold that like the data is Gaussian in any sense, which is why it doesn't really work. Even if these are, that's not like the main part about the t-test essentially. That's not the only reason why the t-test needs normality. The t-test needs normality also for the sample variance distribution, which in this case will not hold for sure.
Yeah. Okay, I'll think more about that.
It's okay. I can talk more about it. So like for the t-test, like when we have a t distribution, it's like this divided by like this over the degrees of freedom, right? And we said that like z is normal 0, 1, and like this v here is like I'll put n, chi-squared n, and like z is independent of v when we have a t distribution. The issue when we do this problem is that for this to happen, this will happen with the CLT, right? Like the x bar minus y bar thing will happen with the CLT. It will be approximately normally 0, 1. The problem is that this will not happen with that, because this needs to happen because the sample variance has normally distributed like elements in it. And this is not happening with this data. And we're kind of throwing out information because I know this as Bernoulli. So it doesn't make sense for me to use a t-test. It's like, I'm not 100% sure about this, but it's probably true that you get more power from a test like this than from something like the t-test if you were to use it like blindly. And it actually is Bernoulli data.
Okay, yeah, that makes sense.
Okay.
Thank you.
Okay.
Could you also set this up as like a chi-square test of homogeneity?
Yes, I think you could have set this up as a chi-square test of independence.
Wait, why? Wait,
it's the other one. They're the same. They're equivalent tests, but yes.
Wait, they're different. Wait, I thought there was something like there's like some fundamental difference in like independence and homogeneity.
They have the same procedure, right? So like they give equivalent statistics. So yes, there is differences.
Wait, but like the points will probably be for recognizing the correct like a.
That's true. I don't think chi-squared is on this exam, right? Because
wait, what?
ANOVA.
We know.
Yeah, I think it's only up.
Actually.
Maybe the chi-squared test we did before chi-squared homogeneity and chi-squared independence.
But not the analysis
of
categorical data.
Yes, and another thing, I think I googled this, and it is equivalent because when you have like two groups, this will be
it would be like
this.
Both of them come from
yeah.
one distribution.
The squared of this is going to be the same as the chi-squared distribution that you get when you do a chi-squared test.
Oh, okay.
For categorical data, I think. That's what I read somewhere, but I'm not 100% sure. So it might be true. It makes sense if it is.
But I mean, it would be fine to set it up as that also, right?
I think so. Yes, I think so.
Wait, why do you?
But I probably wouldn't.
Wait, because it's just.
I didn't think about it that way.
It's like you have like, because the example they gave in like the textbook for that one was like you had like two columns like married once and married more than once, and the rows were like college or no college.
Yep.
So this would just be like witched or unwitched, and then like so the number with success and failure.
Yes, so that's probably reasonable, and you could do that, and I think that's fine.
Okay, just checking.
Yeah, of course. I think like there's a lot of there's no real correct answer for this question,
Okay.
and I'm just more used to doing it like this. I think than other ways, but I think that way is valid. Yes.
Thank you.
And it might be equivalent. So yeah. Okay.
Cool.
Okay. So next question, question 5. I'm gonna try and do this in essentially a nice way that's not too confusing, but there's a lot of notation in this question, and it might end up confusing. So please stop me and ask questions. I'm essentially going to change the notation that's used in the question to the notation for ANOVA because there's a lot of weird kind of notational quirks in this question. And I think it makes sense. This is essentially ANOVA, but with ANOVA we did it for means, and this is for multiple variances instead. That's the only difference. So this is problem 5. So what we have here is, I'm essentially going to restate the entire problem, but we have j equals 1 to j groups. Sorry, not what I'm doing here. I equals 1 to I groups, right? And then j equals 1 to ni elements in each group. So observations in each group, obviously the observation. And they're all normally distributed. They each have possibly different means and different variances. So what we're going to have here is that we're going to have xij is going to be distributed and they're going to be independent, normal mu I and sigma squared I. So we don't know the mu i's and we don't know the sigma squared i's either. And we're interested in testing sigma squared 1 equals sigma squared 2 all the way to sigma squared I of them. And I'm going to call this just sigma squared. for ease again of understanding here. So we now need to essentially get the MLE for both mu I and sigma squared I under the null and under the alternative. The alternative is simply not the null, which is just one of them. I mean, at least two of them are not equal to each other. So are there any questions about the setup here? Okay. It's probably gonna get pretty like here. So first of all, for ease of differentiation, I'm just going to write sigma squared equal to like tau. So I don't have to do derivatives of sigma squared and get confused with the power. So our likelihood here, and this is essentially, I'm going to write a general likelihood without under the null or whatever, is simply going to be a function of mu1 all the way through mu I, as well as sigma squared 1 all the way through sigma squared I. And these are all Gaussian, so this is just a product of Gaussian densities. However, it's a double product, a product over all of the groups, and then a product over all the observations within each group. So what that is that's the product from I equals 1 to I, and then j equals 1 to ni of 1 over root 2 pi, I'll write it separately, times the root tau, or tau to the 1/2, same thing, times the exponent of negative 1/2 xij minus mu I squared over tau. Okay, so let's take a log and get the log likelihood, because we certainly don't want to deal with this by itself. And the way we can do that is immediately when we take a log, the log of the products becomes a sum, and it's going to become a double sum, and we can just distribute the log into here. So I'll try and do this slower than that, but essentially ln here is going to be the sum from I equals 1 to I, the sum of j equals 1 to ni of the log of this entire thing. So 1 over root 2 pi, and I'm going to write this as tau to the negative 1/2. It's the same thing as before, just so that we can see for the next step what I do. X negative 1/2 xij minus mu I squared over tau. Okay. Now the next step I'm going to do again is I'm just going to distribute the log. So I equals 1 to I, sum of j equals 1 to ni. And sorry, my bad. This should be all tau i's, and this should say tau instead of sigma squared. I do not know why I wrote that. So yeah, the taus are indexed by I because they're the same as the sigma squareds. They're just without the square. Okay. So at this point now, what we can do here is we can essentially split this into two main parts. First of all, three main parts. The first will be this log of the 1 over root 2 pi. The second will be this element with the tau I, and the second will be this, which will have the exponent undone, the exponential undone. So this is going to be log of 1 over root 2 pi, which is not going to matter with the derivative, minus 1/2 log of tau I, and then minus 1/2 xij minus mu I squared over tau I. Okay, are there any questions so far about getting here? Okay, so the next step is let's first deal with under the null. So under the null H naught, we have that all of the tau i's are equal to just the main tau for all I essentially. So what that essentially does is that we can simplify this likelihood a bit. So I'll write L under the null here, and we can simplify this. First of all, I'm just going to distribute the sum to this, and I'm just going to call this C because it's some constant. It doesn't depend on anything that we care about. So this is just equal to some constant minus 1/2, and I'm going to write the double sum as like I comma j, so I don't have to keep writing double sums of log tau minus 1/2. Actually, I'll write both sums. The sum over the i's and the sum over the j's, but I won't write the top index. And this is also minus 1/2 the sum of the i's, the sum of the j's, xij minus mu I squared over tau. Now, first things first, let's get the estimate for mu I under the null. So I'm going to take the partial derivative of this with respect to a specific mu in the summation. So I'm going to call this like uk. So this is like a specific mu, one of the j mu's. So what that does is that each of these elements of this sum only has one of the mu k that I'm interested in. So all of the other sums go to 0. Oh my God, sorry. Okay, I'm sorry I missed all these questions. The tau I represents the different variances. I just called the sigma squared tau because we're just testing if all the variances are equal. Yeah, so this is a generalized one. Yeah, I just didn't write anything essentially. Yeah. So now under the null, I'm calling it. Sorry about the confusion. If I don't respond, please just like, you can raise your hand or whatever, and I'll also answer. So I'm going to take this for a specific mu. So like I said before, out of this outer sum over the i's, it's going to go away. I'm only going to have one of them because I'm taking it with a specific k. So what that essentially gets me is that this is going to be 0 because it's a constant. This has no dependence on any mu, so this is also going to be 0 with the derivative. And so all that's going to happen is this, and this summation is going to go away because, again, I'm taking respect to one specific mu. So all that matters essentially is this term and the single element of the sum that corresponds to k from this. So this is just going to be equal to negative 1/2 times 2. Negative 1/2. The sum over the j's still stays. And this is going to be j equals 1 to n, the specific nk that we were looking at. Xij minus mu with the k that we're looking at, times 2 times a negative 1 here from the inside. And again, the tau will stick with us here. The bottom is just a constant. Okay, are there any questions about this so far? So we set this equal to 0 to get the maximum because we maximize at this. And essentially what's going to happen, we can cancel a tau. We can cancel these two 2's. This negative cancels with this negative here. And so we are just going to get that therefore essentially mu I hat under the null, which I just called mu I hat, is just going to be equal. If you just rearrange this, you will just get that this is equal to 1 over nk, sum of j equals 1 to nk, xij, which I believe in the thing is just called x bar I. Or x bar. Sorry, this should be a k now. This is an I. Are there any questions with the mu? Okay, great. The next step is to do the tau. So we have to go here and, back to here, back to this likelihood, and I'm going to do derivatives with tau now instead. And so now this is essentially treated as a constant, but I keep both sums because the tau stays. In fact, this has no dependence on I or j, so we can just distribute this sum. So I'll probably do that. So partial L H naught partial with tau. This is just going to be equal to, I'll write everything out actually. Negative 1/2, the sum over the i's, the sum over the j's of 1 over tau. That's from the log. That's from this log here. And then this here, again, these are just an entire constant in this case. We just have to think derivatives like this, which is just negative 1 over itself squared. So we get plus 1/2, the sum over the i's, the sum over the j's, xij minus mu I squared divided by tau squared. And now the sum of the i's and the sum of the j's all together make the group like sample size, which in this case is just n. So I'm just going to write this as n over tau. And so again, we need to be equal to 0 to maximize it. And so what this is going to get is that what's going to cancel here, this tau, this 2 here, and one of these taus here are going to cancel. And so the estimate here, we're going to get tau hat, which equals sigma squared hat, I just defined the sigma squared, is just going to be equal to the sum over I equals 1 to I, the sum of j equals 1 to ni xij minus mu I squared over n. Okay. Now, for the first part of this question, they give it kind of in a different way than this. If you look at the, maybe I'll share it. If we look over here, what this is, they give it like these two forms here. I already gave this form here. But in the interest of time, I'm not going to convert it into this form, but it is literally the same thing. You just have to multiply this, the definition of this sample variance, and you will get that. So that's under the null, under the alternative now. And I'm going to try and go a bit faster here, especially for the mean, since it is essentially the same computation. Now, under the alternative, we have no restrictions at all, so we have to let the taus now vary with their index I. And so we can go back to like this here, or we can essentially go back to this. So I'm just going to essentially copy this here, but I'll just replace the tau with the tau I. So now this tau has an I index, this tau has an I index as well. Now, for the mu k's, again, I'm going to take respect to a mu k. This is again 0, this is 0 with the derivative, and we get rid of this sum again. So we're going to have this tau k sitting here, but you're going to see why it's not going to matter, because we're simply going to get that this is the sum over the j equals, j equals 1 to nk of xij minus mu k divided by this tau I, and this needs to be equal to 0 to this tau k actually. But this tau k has no dependence on any sum here, we can just get rid of it. This tau k is going to cancel with the 0 here, so we can get rid of that. And then again, we're going to get that mu hat I is just equal to x bar I, the same as before. So there's no change here. Are there any questions about that? Okay, and then the next part of the question is simply asking, well, that's the trickier part, I guess. But again, we're going to have the same likelihood here, but with the tau i's. And so partial alternative, this is going to now have i's here. That's the only change. And so under the alternative, with respect to now, I'm going to do the same thing I did with the mu's. This is a specific k. So again, all of the outer sums will go away, which is key in this case. So this is 0, this outer sum goes away, and we just get this essentially sum here that we have here. So this would be negative 1/2 over, negative 1/2, the sum from j equals 1 to nk of 1 over tau k. And in here, the same thing's going to happen. We're going to get rid again of one of the sums. We get negative 1/2. We have a plus 1/2 here of the sum from I equals 1 to I. Nope, no sum from I equals 1 to I. The sum from j equals 1 to nk, xij minus mu k, and this should be k, and I think I've forgotten that before, divided by this tau k here, squared. And so this is going to be equal to 0. Again, the 2's cancel. This tau and this tau cancel. Now, this becomes just the sum to nk. So this just becomes negative nk plus this sum from j equals 1 to nk k squared divided by tau k. There's no outer sum for the tau k to follow. And so when this equals 0, we get that tau hat I, or tau hat k, equals sigma squared hat I. What do they call it? Hat hat in the book, in the final. And that's just going to be the sum from j equals 1 to nk xkj minus mu k squared over nk, which is exactly what they give if you just transform it a bit. Okay, so are there any questions? That is part 1 done. Okay. Part two. That's probably the worst part of this entire section. So to show that this becomes like that likelihood ratio, we essentially are going to need to put in this into a likelihood ratio. And so the likelihood ratio is the likelihood under the null divided by the likelihood under the alternative. Yeah, I think it's that, yep. So it's likelihood under null of likelihood under alternative. So in that case, lambda is equal to, we have to again write the sorry, this question. Was the MLE of the alternative found to solve part B? Yes, I think so. What do you mean by part B? Yeah, the math likelihood under the null and under the full set. Yeah, exactly. Yeah, sorry, I meant the likelihood under the alternate or the null. I keep saying stuff like that. But yeah. Okay. So and this should be union the null. Thank you for pointing that out. That's my mistake. And this should be the maximum, of course. But yeah, I didn't write that. So if we were to write this out here, we get again the same likelihood that we had before, which is now the double products of Ni. And what this will essentially have here is that I'm going to ignore the actually I won't right now, but there's 1 over root 2 pi, which is not going to matter because it's a constant present in both the ratios. And then we're just going to have 1 over sigma just sigma hat, or which we had before, x negative 1/2 xij minus mu I hat squared divided by sigma hat squared, and this is going to be divided by, again, this product here. This needs to have now 1 over sigma hat or sigma hat I, because they're dependent on I now, and then x of negative 1/2 xij minus mu I hat squared divided by sigma hat I squared. Okay. First things first, what can we cancel in this scenario? Well, we can cancel this and this. Second things off, we are essentially going to distribute the sums here, and because I'm running low on time, I'm kind of going to skip this part a bit, but what's going to happen is that if you notice this and this in here are essentially these up here without the sums that belong to it. So when I distribute this product in here, it will become a sum, and these will just cancel, and I'll just get like an exp of negative n over 2, essentially. And that same thing is going to happen in here, because only one of the sums will properly distribute that we need, and we'll get the same thing. So this is just going to be essentially 1 over sigma hat, and this will now essentially get, because of these products, it's going to get this, it's going to be sigma hat squared to the n over 2 times this x of negative n over 2 here. And then we're going to get this 1 over, we have to keep one of the products here because this depends on I. So this product can be shifted into the denominator, and then you get pi I, sigma I hat essentially. And this will be to the power of ni over 2, which from this will be squared. And this comes from this product here. And again, this would just become the x of negative n over 2. So this cancels, and we just get, if we just flip them the way that they are, the product from I equals 1 to I of sigma hat squared I to the ni over 2 divided by sigma hat squared to the n over 2, which I believe is essentially what they have there, except they just replaced the estimates that I didn't write in. Are there any questions about this part? Yeah, so this is a very algebra heavy question. So I guess I'll give like a tip about this question. If you see a question like this on a test, and you're not confident in your algebra, you should probably like either, actually I'm not giving good advice, like save it for last, or just like, because you know the answer, you can try and like skip steps essentially, which is essentially what a big algebra bit. This is essentially the entire part. And I'll post these notes. Yes, Wenhao, yeah.
So for the simplification in the exponential, do you just plug in the sigma hat and sigma hat, so you can get essentially this n/2?
Yes, you'll get that. Yeah.
Okay. Also, I think you need to decide the sigma hat is in terms of the simple variance hat. Sorry, simple variance square.
Yeah.
Don't you also need to like plug in that formula?
Yeah, you can't plug it in. I just didn't plug it in, but yes, if you just plug in the ones that you get from the question, you'll get the exact answer that you need.
Okay.
I'll plug it in now, but yeah. Okay, to clean up the exponential, in this case, the first case numerator, this just gets these powers, right? Because they have no dependence on the products. But then this distributes onto this exponential, and the product of the exponentials is the sum inside of it. So you can bring the double sums inside here. And this is a constant. But this double sum essentially equals this constant without some of the n's that are there, without this like n factor here. So these are going to cancel when the products come in here as sums. And essentially the same thing happens here, but because there's an I here, it's a bit different. Only one of the sums distributes this fully, this J1 essentially. But that's all we need to cancel. But yeah. Okay. Because I'm running short on time, I'm going to go on to the next part. But essentially, if we look at the definitions for the sigma squared double hat I, that they tell us is just ni minus 1 si squared over ni. And this again, we just keep this ni over 2 power. I didn't move that, that's just from here. And then we just divide by this to the n over 2, and the sigma hat squared already has this sum. And again, this is kind of why there's a lot of notation like switches in the question, which is why I'm trying to keep my notation constant. But I'm writing I equals 1 to the big I of this si squared. And this again, we keep this n over 2 that we have here. And that's how you get that question. Okay. The third part. So they say we assume k equals 2. So this is now part 3. We can assume now that I equals 2, and we want to get this just in terms of the ratio of the two sample variances. So I'm going to try and do this relatively quickly here. But essentially what we have is I distribute this product here, and I just distribute this sum here for two samples. And the key thing to note here is that like n1 plus n2 equals n. That's all we need to know for this part. So let's do that. So in this case, lambda in this case, again, it's just gonna be the product of two of these. So I'm just gonna copy this. It's just this. Another one of itself, except this is just going to be n1, and this is just this also is the 1, and this is just going to be n2. There's a 1 there, an I, and that needs an s2 n2. Okay, so that's those right there, and then the denominator is just the sum. So it's these two same terms, just summed. So we get n1 minus 1 s1 squared over n1 plus n2 minus 1 over n2 s2 squared, and this is divided over n over 2. Now I need to get this in terms of the ratios of the sample variances, which is not that terrible. again, the key assumption that we need is just this. So we can like simplify this denominator here a bit and then bring it in here, and I can get it in terms of like a function of these ratios, essentially. So what we can do is, shoot. Yeah, so we can rewrite the denominator as this, n1 minus 1 over n1 . So we can have this, and I'm going to put this to like the n1 over 2, and then I can have this the same thing again to the n2 over 2. That way, essentially, I can like bring these under the same exponent to simplify. So therefore, I'm going to take this essentially in like two parts. I'll take this divided by this, and then this other one is it's the same thing, but like flipped because it's just symmetric. So n1 minus 1 over n1 s1 squared over, we then get n1 minus 1 s1 squared over n1. And this will all be the power of n1 over 2, but we can simplify this luckily here. Yep, hopefully I did this right here. Yeah, so we can essentially write, did I do this wrong?
I think it should be n for the denominator.
No, the denominator should be like, it's because I factored it like this. I think it's still right. I just have to remember if this needs to be negative. This is fine because what I did is I like split this denominator into these two, right? So that I can like bring this here. Maybe somebody different than me, but.
I mean, like from the part 2, right? So in the part 2 for the denominator is a sum of like the n1 minus 1 times s1 squared over n. Why it is like over n1?
Oh my bad. Yeah. Sorry. Yes, thank you. I get what you're saying. Yes, thank you. I think I missed that the entire thing. Thank you. Yes, that's right. Okay. But besides that, this makes sense. Okay. So essentially, if we kind of like flip this, this will become like a negative here. I get that this equals, this is like horrendous to write. Yeah. Plus n2 minus 1 over n s2 squared divided by 1 minus 1 over n1 s1 squared. Power of negative n1 over 2 now. Now we can like kind of like cancel these and get this in terms of the ratio finally. So that's kind of my goal here. So this will just equal n1. Sorry. Yep. n1 plus n1 over n plus n1 over n. Yep. n2 minus 1 over n1 minus 1 s2 squared to the negative n1 over 2. Sorry, and there needs to be the ratio here, I forgot. s2 squared over s1 squared. So that's now in terms of the ratio of the sample variances. And kind of like I said before, I did it for this side with this one. It's essentially the same thing, but we just switched the n1 to the n2 for this side. So do the same for the right side. And the right side will just be the same thing, but it's going to be n2 over n plus n2 over n, n1 minus 1, n2 minus 1, s1 squared over s2 squared to the negative n2 over 2. So now the entire point of this question is essentially to see that this entire thing just depends on this ratio here, either the inverse or itself. It doesn't really matter. So this entire depends, and it doesn't really matter which way you put it. S1 squared over S2 squared. That's just the key kind of assumption that here. My AirPods are going to die. But what does that mean in terms of a test? We can know the exact distribution of this because this is going to be chi-squared. I mean, sorry, these two are chi-squareds. So each SI is chi-squared, so the ratio is F. And that gives us a test statistic that we can use to test the hypothesis that all of the variances, the two variances, are equal. So this is like an F test. And that doesn't require any asymptotic theory in this case. And I believe the degrees of freedom is just going to be n1 minus 1 comma n2 minus 1. And so that's that. Are there any questions about this this question? I'll talk about problem 4 afterwards. Yes.
Yeah, I thought in the ANOVA when we get the F test statistic, we divide the chi-square test by like n-1 or something.
Yes, it's
Do we
that's
need
there
to-
too. It's like here, right?
Oh yeah.
Yeah, you can do that as well. Yes. Yeah, that's the chi-square. Yeah, with proper scaling. Essentially, that's
Okay.
going to happen. Yeah, those are just constant scales, though. That will essentially become a chi-squared then.
Yeah. So we still need to scale the S1 square and S2 square by certain amount to get F distribution.
I think you just have to multiply them by this, actually. If I need to remember exactly what it is. That's my problem. I didn't write it down. But yeah.
Okay.
Yes, if asymptotic theory was allowed, you could just use -2 log lambda is like chi-squared with degrees of freedom, proper degrees of freedom. But they said no asymptotic theory, so I had to simplify in terms of a test statistic and figure out what the test statistic was. And it's like F. That's why. That's the point of this question.
Sorry, what would be the degree of freedom in that case then?
In the case of the -2 log lambda,
Yeah.
it's like I need to remember actually what it is. It's like the dimension. I don't remember the formula. It's like the dimension of the whole thing minus the dimension under the null, right, or something like that. Yeah. So
Right.
it's like I minus 1, I think, then, right? Like the total number of groups, because under the whole thing you estimate I things, and under the null you estimate one thing. So I think it should be just I minus 1. I'm not wrong.
Are we also estimating mu's?
Yes. Sorry, you're also estimating mu's under both. So it's actually I mu.
Oh,
I didn't
then
think about this,
both
actually.
mu's cancel out.
Oh shoot. I need to think about that. Oh, they do cancel out. Yeah, they do cancel out. I think actually, because they're both being estimated, both null and alternative. They're going to cancel out. That's right. I think if I'm not going crazy. But like, yeah, that's kind of. Does that make sense?
Yeah, thank you.
Yeah, of course. Okay, so for question 4, we can just bootstrap. We can just bootstrap this essentially. We've imposed. I mean, actually, sorry, a non-parametric approach testing the hypothesis. We can essentially try to bootstrap. That's kind of what we want to do here. I actually think about this question a lot. But yes, you could probably essentially. What do you think about bootstrap now? You could still take the ratio of the sample variances and just bootstrap that. And because this kind of is a good indicator of whether the variances are large or not, so we could just bootstrap the ratio of the sample variances to try and see which of them, what that is, and then try and reject, even if we had no idea what kind of distribution it came from. I don't think that there is a clear answer though. That's kind of my answer there. That's usually my answer for kind of non-parametric stuff. Okay. So problem 6. Problem 6, I'm going to just remind people about the assumptions from linear regression that we typically use. Yeah, the F-test of equality of variances. That's this one for 2 cases essentially. And I think it has the same statistic. But yeah, this is like, I guess, a more general version, at least like the one on top, because this is more than 2. Yep. So for problem 6, when we have a linear regression, we're generally going to assume that the model is going to be something like, at least in one dimension, it's going to be like beta naught plus beta 1 xi plus some epsilon I noise. And this is not really essential for least squares to be done. However, this is kind of like when we do it. You can tell do least squares on anything, but like if we take a look at each of the plots here, one looks like a line, a straight line, where we kind of add noise to it, and the noise is constant variance, and it looks good. Two looks like a quadratic fit, so I wouldn't say that the least squares approach is the best for this, unless you're doing like a natural quadratic fit. But like a straight line here doesn't work. Plot 3 is probably the most divisive. The only issue is that we have an outlier, which least squares is notoriously bad at dealing with. We can see that the entire line is shifted to like deal with it. So in this case, least square is probably not the best. It's probably better to do something like absolute deviation, or evaluate whether this outlier is actually meant to be in the data set or not, because it's pulling the line so much up, and the rest of the data points are essentially being penalized for it because of the squaring of the least squares. Question, plot 4 does not look like it's least squares at all, really. In fact, this entire point is shifting the entire line. So least squares is not good at all for this one. So I think 4 and 2 are clearly yes.
For plot 3, can we say we can try to consider get rid of the outlier?
Yeah, yes, you can probably say that we try to consider an outlier. But like, if you just say like least squares is very bad with outliers, that's probably good.
Okay. So I wanna say like after get rid of the outlier, I can refit the regression line to the rest of the data. And
yes, you can see that that's like a bit of a controversial statement because we don't know if the outlier is actually like meant to be there, and if there's not any other chance of outliers. Essentially, like we have to be kind of careful with that. We shouldn't just throw out outliers. That's like a very advanced thing for this course anyway. So like if you just say least squares doesn't do well with outliers, maybe we should consider something else. It's probably fine. The question's not asking for like alternatives anyway, I don't think.
okay.
Yeah. Well, the same argument for plot 4, like getting rid of the outlier. Well, if we got rid of that outlier, I don't even think that this would be able to fit the line. Like the rest of the data is like a vertical line, right? So the slope would be infinite if we tried to fit that. So I don't think that would work. Like this data is just not like good for like our assumption here, kind of. But yeah,
I could just put something. Plot 4. I think the main point is that the issue is that there's only 2 values of x. But there's nothing wrong with the residuals for x equals, I guess, 8. And there's only 1 point for x equals 18, which isn't a problem by itself. But the ultimate problem is that there's only 2 values of x. So that's the issue. And then, yeah, I think even in plot 3, like plot 2 is obviously like there's a pattern to the residuals. Plot 3 is just that it's not homoscedastic, right? And yeah, there's just this one residual that's huge. Yeah. That's all.
Yeah, sounds good. Okay, so that's pretty much that. I'll stick around for questions for like 10, 12 minutes.